So I'm going to talk a little bit about the science with Planck, and I have to do it in less than less than 40 minutes.
You'll practice right.
Anyway, I want to leave enough time for the tension to build, although I'm already pretty tense, and I guess some other people are as well. Planck. So this is now the other satellite, the other telescope that's sitting underneath Herschel on that rocket. And Planck is different from Herschel in that it is not an instrument that is going to do a number of different things astronomically. It has one goal and one goal only, and that is to map the entire sky, map the cosmic microwave background over the entire sky. It's a mission to study the cosmic microwave background. This is an artist's conception of the Planck telescope, and this is an artist's conception of the cosmic microwave background, what the full sky map would look like. And this is a picture of Planck, similar to the one Pete showed, just before it was mounted in the rocket. And the reason for doing this is to try and answer the question or find out more information about the question, where did we come from? Where did the structure and the galaxies and all of the objects that are going to be detected by Herschel, where did they originate? What was the origin of structure formation? So this is the science of cosmology, is trying to understand the overall evolution of the universe. And some of the big questions in cosmology, I mean, there are many, many big questions in cosmology, but some of the big ones are, what is the fate of the universe? What, if it exists, is dark matter? What, if it exists, is dark energy? What is the topology of the universe? What processes generated initial conditions in the universe that led to all of the things that we observe today? So one model, which is currently the most popular model for answering some of these questions, is called inflation. Inflation refers to a rapid expansion of space in the very early universe. And this is necessary or is useful in order to explain the observed uniformity of the universe. In other words, the universe that we observe today, even though it contains lots and lots of different things in it, it actually, on large scales, is quite uniform. If you look in one direction, you see the same types of galaxies as you see if you look in another direction. Now, the other thing that inflation, this rapid expansion, and the end of this expansionary period does, is it provides a way of generating tiny fluctuations in the early universe that are necessary to form all the structure that we see today. And this just shows sort of an idea of the timeline of the history of the universe, according to the theory of inflation. So as Steve mentioned, one of the things that's really important for this science of cosmology is the fact that as we see objects that are further away, because light travels at a finite speed, we're looking further back in time. So if we look far enough away, we can see all the way back to close to the beginning of the universe. So how far back is it that we can see? Well, the universe, it turns out, is extremely transparent. The room is very transparent here. So you, at the back of the room, may be able to see what's happening on the screen here. But the universe is much, much more transparent than that, because we can see stars, for example. If you go out at night, you can look and see stars. Stars are incredibly far away. So it's really quite amazing that the light that comes from a star, even the nearest star, which travels millions and millions of miles, makes it to the Earth without being interfered with. But that's not all. The universe is so transparent that light that comes to us from 13 billion light years away is completely unimpeded, and it arrives, well, aside from the small amount of space that is occupied by galaxies, even though there are so many galaxies, as Steve mentioned, they're not enough to impede the light that comes to us from the very distant universe. So we're at the center. If you look out all around in the universe, you can see out to very, very far distances. And what you see is at the edge, at the very edge of the universe, you're seeing so far back in time that we're seeing back to a time when the universe was so hot and so dense that light was no longer transparent, light was no longer able to travel unimpeded. And this is known as the surface of last scattering. It's like a wall. It's like the walls of the room. You can't see farther out than the walls of the room. You can see all the galaxies and all the people inside the room, but then at a certain point, you're at the very edge, and that, in astronomy, is the edge of the universe. And so if you scan around like that, you can make an image. So this wall is known as the cosmic microwave background, or the surface of last scattering. And the cosmic microwave background has been known about. It was predicted originally in the 1940s which is about the time when the theories of the Big Bang and the expanding universe were really coming into their own. But it wasn't discovered until about 1965, when it was discovered by Penzias and Wilson, using a radio dish. And what they discovered was a uniform glow, uniform radiation that came from all directions. And it had the same brightness, which they expressed in terms of a temperature. They won the Nobel Prize for this discovery in 1978. And then, until about the 1990s, not much more was known about the cosmic microwave background. It was generally seen to be a completely featureless thing. It was uniform in all directions, aside from a slight difference in the brightness looking in one direction versus the other. But NASA launched a satellite called COBE in the early 1990s, intentionally, like Planck, to make an all-sky map of the cosmic microwave background, which it did, and it measured this, which I'll show in another minute, a little bit larger. And for that discovery, the leaders of the COBE instruments were awarded the Nobel Prize quite recently in 2006. Now, since COBE, in the last 15, 20 years, there's been quite a lot more that's been learned about the cosmic microwave background. Higher resolution measurements have been made, and from these measurements, we've learned a lot about the universe, especially about the evolution of the universe and the early universe. And now we're poised to learn even more with Planck. So what does the microwave sky look like? The cosmic microwave background looks like, as I said, it's a uniform glow. If you turn up the contrast, you see this dipole. This is the hot-cold signature, which is actually due to our motion, the motion of the Earth with respect to the surface of last scattering. You can think of it as being due to the motion of the Earth with respect to sort of the average motion of all of the matter in the universe itself. So the Earth is moving at some velocity with respect to the average zero velocity reference frame. And then down here, if you turn up the contrast even more, you see something that looks like this. This shows an image of the CMB, the all-sky. This is the kind of thing that Planck will produce. In the middle, you see this galactic plane. This is emission from our own galaxy, which is still present at these wavelengths. But then out here, there's no emission from our galaxy, or very little, and what you're seeing is the intrinsic brightness variations in the cosmic microwave background itself. Now, these variations, as Pete Hargrave mentioned, are very small. They're on the order of 100 or 10s to 100 parts per million. Just to give you an idea, the variations in the surface of the Earth are about 1,000 parts per million. So it's the Earth, compared to a sphere. So the Earth, from space looks very round, but it's much less round than the cosmic microwave background is uniform. So what's happened since COBE is there was another satellite launched by NASA called WMAP in 2001, and that made this image of the sky. And you can see this is an improvement. But Planck, which is about to be launched, will improve on this by more than an order of magnitude. And that will really enable a new level of sophistication in understanding of the early universe. So just to finish, some of the things that are measured, or some of the things that we can use the cosmic microwave background to help us determine, are some of these parameters here, like the overall curvature, as I mentioned, the shape of the universe, the age, the composition of the universe, and the expansion rate of the universe. And then I'll just end with this thing, because we're already getting very close to the financial results. So hopefully their financial results are good. But Planck, which will make this map of the full sky, the most detailed CMB survey ever, has the potential to revolutionize physics. It's possible that Planck might discover evidence of new types of matter, or at least tell us more about the possibility that there exists dark matter and dark energy. It's possible that Planck could tell us something about the size and shape of our universe. And it's also possible that we could learn about the physics of the very, very early universe. We could constrain models of inflation or any other processes that might have been present that actually led to the structure that we see today. So all of these things are very fundamental. Planck has one goal. The goal is to map the sky, and it's going to do that, and then from that data, we hope that we can learn something about these very basic questions. So hopefully, we will see quite soon.
So about 5 minutes.
If it's successful. So that's all from me.